Multiplication of a vector by real number. When we are multiplying a vector with a positive number, we obtain a vector whose magnitude is increased by the factor of that positive number and the direction remains the same. That is, suppose we are multiplying our vector with the number lambda. Then the magnitude of the vector increases by a factor of lambda and the direction remains the same. For example, here is a vector A, and when a real number 2 is multiplied with A, we obtain a vector whose magnitude is twice the magnitude of A, whereas its direction is in the same as of A. Now, when a vector is multiplied with a negative number, then we obtain a vector whose magnitude is increased by a factor of that number, but here the direction will become the opposite. For example, we are having a vector A and we are multiplying this vector A with the number -2. Then the magnitude of our vector doubles because the number is 2, but the direction becomes opposite. So this is how the vectors act when we multiply the vectors with a real number. Addition and subtraction of vectors. If we have vectors A and B in a plane, then we can obtain the resultant, that is the addition of two vectors, vector A plus vector B. For that, place the vector B such that its tail is at the head of the vector A. Here we are having two vectors, vector A and B, which are placed in a plane. Now we are taking the vector B and placing it at the head of the vector A. If you observe, you can see here the direction or the inclination of the vectors are not changed, but the vector B is brought to the head of the vector A. The tail of vector B is placed at the head of vector A. After placing in such a way, the line joining the tail of vector A to the head of vector B gives the resultant of vector A and B. That is, the resultant vector R is equal to vector A plus vector B. So the line that joins the tail of vector A to the head of vector B gives the resultant vector, and its direction is towards the head of the vector B, as you can see in the diagram. So here we can see that we are arranging the vectors in such a way that the resultant forms a triangle altogether. Therefore, this method is known as triangular law of vector addition, or it is also known as head to tail law of vector addition. Now, how can we subtract such two vectors in a plane? Suppose we have to find A minus B here. What we do is we reverse the direction of B and then we apply the triangular law of vector addition itself. That is, we are having vector A and vector B here. In order to find A minus B, we just reverse the vector and draw the minus B vector. Here we have obtained vector A, which is kept as such, and vector B is reversed in its direction. Therefore, this becomes minus B vector. Now, applying triangular law, we are taking the tail of minus B vector to the head of vector A, that is, vector A and minus B vector is this. Now, when we apply the triangular law, we join the tail of vector A to the head of vector B, that is minus B, and the resultant is A minus B, because this is the vector minus B. And here the resultant from tail of vector A to the head of vector minus B is the resultant, which is A minus B. So this is how we subtract the vectors using triangular law of vector addition. Another very important law of vector addition is the parallelogram law of vector addition. Here what we do is we are bringing the two vectors, taking their tails and bringing them to the common point. Then we draw parallel lines of both the vectors and we form a parallelogram altogether. Here we are having the two vectors. If you can see, the tails of the two vectors are placed in a common point. And we draw parallel lines to both the vectors. That is, vector A is here and a parallel of this vector A is drawn and a parallel of this vector B is also drawn. So altogether we get a parallelogram. So our vectors A and vector B are acting as two sides of the parallelogram. So whenever we are applying parallelogram law, we place the vectors such a way that they are the two sides of our parallelogram. After placing the vectors in such a way, the diagonal of this parallelogram from the point of intersection of vector A and B gives the resultant of the vectors A and B. That is, resultant is equal to vector A plus vector B. So this is how we represent the resultant of vectors using parallelogram law. Now let us see what is the magnitude of this vector. We have seen how we can represent and give the direction of this vector. Now numerically, what will be the value of this resultant vector? In order to get the value of the resultant, we have to get the magnitude of this diagonal of the parallelogram formed by the two vectors. For that, we extend the vector, that is the one side of our parallelogram, and we join a line which is perpendicular to this. As you can see in the diagram, we have a parallelogram PQST which is formed by joining two vectors and their parallel lines, and from Q we are drawing a perpendicular, and the vector A, that is TS side of the parallelogram, is extended, which meets the perpendicular OQ. So we have extended our parallelogram in a small way. Now we obtain a right angle triangle here, if you can see. So here we have taken the angle between vector A and B as theta, and if you can see, this is also equivalent to the vector B, and it is also making angle theta similar to the angle between A and B. This is the extension of vector A and this is vector B itself. Therefore the angle here made is theta. Now we are having two right angular triangles, that is QOS and triangle QOT. There are two right angle triangles. Now we know that using the right angle triangle QOT, we can write the resultant is equal to QO square plus TO square. Here we write from the triangle QOT, TQ square is equal to OQ square plus TO square, and we know that TO is TS plus SO. So TO is written as TS plus SO. So TQ square can be written as OQ square plus TS plus SO the whole square. Now expanding this, we can write, we know that TQ is the resultant, so we can write it as R square is equal to OQ square plus TS square plus SO square plus 2TS SO by applying A plus B whole square formula. And we know that from the small right angle triangle QOS, we can write OQ square plus SO square is equal to SQ square by applying Pythagoras theorem. OQ square, that is one side of the small right angle triangle, plus SO square, the other side of the triangle, we obtain the hypotenuse square. So OQ square plus SO square gives the SQ square, and as we told, this is similar to the vector B. So SQ square means vector B square. So SO square plus OQ square gives the vector B square. If you observe here, we are having an OQ square and SO square. So both these forms SQ square. So we can add these two terms and write SQ square here. So the expression now becomes R square is equal to SQ square plus TS square plus 2TS SO. And we know TS, that is this, is the vector A, and SQ is vector B itself, and now the unknown is SO, that is this small extension. To get the small extension in terms of the vector, we use the small right angle triangle, and from that we write cos theta. Here if we apply trigonometry, we can write cos theta is equal to adjacent by hypotenuse, that is SO by SQ. Therefore cos theta is equal to SO by SQ, from which SO is equal to SQ cos theta, and we know that SQ is the vector B itself. Therefore we can write SO as B cos theta. Thus here the whole expression becomes now R square is equal to SQ square plus TS square plus 2TS SQ cos theta, and that can be written as B square plus A square plus 2AB cos theta. So the final expression for R square, that is the resultant square, is obtained as B square plus A square plus 2AB cos theta, from which we can write R is equal to root of A square plus B square plus 2AB cos theta, where theta is the angle between vector A and vector B. So if we are having two vectors A and B making an angle theta between them, then the resultant of these both can be obtained as resultant R is equal to root of A square plus B square plus 2AB cos theta. Now to obtain the direction of this resultant vector, we know that the resultant vector is obtained in an inclined way between both this A and B, and let the resultant vector is making an angle alpha with one of the vectors. So by knowing this alpha, we can tell the direction of the resultant vector. We know that here, taking the bigger right angle triangle, that is QOT, from which we can write tan alpha is equal to OQ divided by TO. OQ by TO is the tan alpha from this triangle, and we previously said TO is TS plus SO, and we can put that value. For that we have to know SO here, and OQ is also unknown. So we have to convert OQ and SO in terms of the vectors. For that we consider the small right angled triangle, and from which we can write sin theta is equal to, here sin theta is equal to OQ divided by SQ, from which OQ is equal to SQ sin theta, that is vector B sin theta. So OQ is vector B sin theta. Now taking cos theta, we get SO divided by SQ, and from which we can write SO is equal to QS cos theta, and that gives vector B cos theta. So the unknowns, that is OQ and SO, are now converted in terms of the vector. Now we can write the expression for tan alpha as OQ by TO, which is equal to OQ by TS plus SO, and OQ is B sin theta, TS is vector A, and SO is B cos theta. Thus tan alpha is equal to B sin theta divided by A plus B cos theta. This gives the direction of our resultant vector, from which we can specifically write alpha is equal to tan inverse of this expression. So this is how we find the resultant of two vectors and the direction of the resultant.